So we have today and Thursday, and a couple of things to do. One is I wanted to finish up. There were people who weren't here on Thursday last week, and hopefully they are now. So I'll go through that real quickly. And let's see, that's mine. Okay, so let me call out the names of the folks who didn't select a module. So Josue Alcaraz, is Josue here? No? And how about Antonius Bellamy? Antonius? No? How about Tyrone? No? How about Ariel Castillo? No? How about Justice Flod? No? How about Joseph Flint? And how about Aaron Gonzaga? And how about Chris Guillermo? And how about Esteban Marino? Esteban. So you're here, with or without headphones? Okay. So what module do you want to do?
I'll do touch.
Which one?
Touch.
Touch, okay. All right, and then Olajide? No? And how about Alonzo Ramon? Alonzo. Which one? One more time.
The buzzer.
The buzzer. Okay. Okay, and Logan Spahn? Logan? And how about Cheng Su Yu? No? Okay. All right. So, yeah. What's your name?
No, I was here last time for
Yes. I'm sorry, what? Yes. What's your name? Natalie? One, two, oh, here? The ping? Okay. Anybody else? All right. Okay, that's good. All right, so, all right, and then, okay, that's good. And then, so let's see. So what I thought I'd do, maybe I'll do the general part of the final. I'll go through some of those questions. I was working on that on Thursday last week. I'll do that some more. By the way, I did post all the scores, all the grades for the final projects. Everybody did pretty well. So, what's that?
first place?
So I'll announce that Thursday. No, I didn't forget. I already sent the info. We're preparing the certificates and stuff. I don't know. The money probably won't be available until later. So I think the way it came out in here was a first place, 2 second place, and 2 third place were tied. And then I had 2 honorable mentions. I think that's how we did it. So the honorable mentions will get a certificate, and the other folks will get a certificate plus a little cash.
Can I trade the prize, not take the binder?
I don't do it.
You don't have to take the fine. Just get a 0. It's not a problem. Yeah. Look, I hate giving finals. It's no fun at all. But this one really is pretty benign. Sometimes it's useful. In logic design, I give a pretty hard final. But in Micro 1, the emphasis is on the laboratory and the project. So if you did the lab, you did the project, you're in pretty good shape. I did send out an email to everybody who was missing 1 lab or more. So hopefully, if you didn't get an email, then according to Anshul, you're not missing any labs. If you got a thing, then she's going to be in the lab on Thursday afternoon before class from 2 to 4. So that is the last chance to make up labs. And even that, probably we shouldn't do that because we already had the last chance a couple times for the pick labs. But you can make up any lab you want this Thursday from 2 to 4. If you have more than 2 or 3 labs, though, you probably can't get them all done in that 2 hours, but you can try. You can be missing 1 lab, you will still get a grade in the course, and you'll lose about 8 points on your lab score, so instead of 100, you'll get a 92. And as long as you've turned in most of your lab reports, you'll be fine. If you turned in less than, I don't know what we decided, 50% or 60%, then I'll probably take some points off for that. But as long as you turn in most of them, and all those links should still be available. But what really counts is demonstrating your laboratory to Anshul. So make sure you do that. If you're missing 2 labs and you want to get a grade in the course, then you should do that. Are you still receiving me back there? I don't know. I'm tempted sometimes just to come in with, with a big iPad and headphones on and just kind of do that the whole hour and see how you guys would feel. Anyway, it'd be a little strange, wouldn't it? Or we could just play a video. Yeah?
For turning in the report for the project?
Yeah, so what I told you to do on that, there's a template on Blackboard, and I want you to spend 2 hours trying to fill it out as best you can. You don't have, after you've done 2 hours, you can quit. Okay?
I just don't think there's an upload.
Yeah, there's not a link
on
upload.
Blackboard.
I thought I created one.
There's a link for your code.
Yeah, I think I turned up, I think I did, but let me look. We'll check that. Okay, let's see. Maybe I didn't. Maybe there is. Yeah, okay, maybe I didn't create one. My bad. All right, let's do that. Okay, it's there now. And I'm pretty sure it's visible. Let's see, let me move it to the top. Maybe not. That's all right. Can you all see it, I assume?
No. It's in the very bottom.
No, not. I know you can't see this. Yeah, I just moved it up to the top.
Dr. Mark,
Okay, yeah.
is it due on Thursday or?
I didn't put a due date. I put the 10th of May as a due date. So, yeah, just get it in. Okay. So let me get rid of this. Okay, so that's so basically the rest of the time then I'm going to talk about the I'll talk about the test. And let me pull that up. Yeah.
Do you have a practice exam or anything that you'll post or review?
You know, I thought there was one on the web. Maybe it's not visible.
There's a one for the first test, but not for the second test.
Okay, I just killed that. I'll look at that this evening. I'll try and make sure there's something posted. I think there's something on there. Maybe I'll do that at the end of the class, but yeah, let me kind of get on that. And let's see. Okay. All right, so I'll just finish a few more questions on the general part of the final, and then we'll start going through the modules. Okay, so let's see. So the two transistor switch on the Viva board has the outputs connected to the green terminal. So it's basically it connects the battery power. So if you have 5 volts plugged in, then the terminal will switch 5 volts. If you have 9 volts, it'll switch 9 volts. The two transistor switch will probably handle, I don't know, maybe up to 30 volts even. Although the regulator at some point is going to have problems with that at some point. Probably right at 30 volts or something. So anyway, the whole point of that, you can control it with the terminal that's the 2-pin female terminal. Both pins are connected together, and all you have to do is drive that input high, and it turns on that 2 transistor switch. 2 BJTs, a 3904 and a 3906. And all you have to do is drive that pin low or leave it unpopulated, and it'll turn off the 2 transistor switch. So some of you, how many of you use the 2 transistor switch on your project? I know a few people did with the buzzer and stuff. Yeah, is that it? Okay. All right. So anyway, so let's see. So the RGB LED on your project board, on your Viva board, and also for that matter, the one on the KL25Z, is it common anode or common cathode? Yeah, it's actually common anode because you have to turn it on by driving the individual pins low.
Okay, makes sense.
So, okay, and then we typically ran our chip at 4 megahertz. But what's the fastest clock speed you can run the PIC 18F the PIC 16F1829 at? Assuming you're running above, say, 3 point some odd volts. Actually, let's see what that is. I forget. Yeah, let me pull up the data sheet. I'll let you see that. So if we look at the power management, we go all the way to the end. DC and AC characteristics, electrical specifications. So I always forget which it's in. It's one of these right here. See it? Yeah, it's the first one. So what this shows is, so you can only run up to 16 megahertz from 1.8 volts to 2.5. Above 2.5 volts up to 5.5, you can run it at 32 meg. So you have to be above 2.5 volts. So there is a voltage requirement. And this is for the low frequency, and for that you have to be, same thing, you have to be about 2.5 to 3.6 to run it at 32 megahertz. So both of them break at 2.5 volts and 16 megahertz. Okay, yeah, that's good. Okay, so we talked a little bit about stack pointers. So you should know that the PIC had, the mid-level PICs all have a hardware stack of 16 levels, that's all it is, and they don't really have a stack pointer per se. Well, there is one someplace, but it would only be, so we've never really talked about it, but how many bits would the stack pointer be on the 16F1829? It'd be 4 bits, right? Because there's only 16 levels. Whereas a normal stack pointer, like on the KL25Z, it's 32 bits. It's a pointer to a memory location, and all memory locations are 32 bits. The address bus is 32 bits. So, but we don't really, I don't know that you can even write the stack, read or write the stack pointer in the PIC. I don't know if it's accessible. It might be indirectly. I've never actually looked at that. Okay. All right. Okay, and then you should know the core registers. We covered that on the first test. And you should have some idea about the core registers on the KL25Z. On the KL25Z, you should know that you have 13 general purpose registers, and then you have a stack pointer, a link register, a program counter, and the status register. And that's it. That's all you really have to know about. You should know that the status register has the status bits, and there are 4 of them on the KL25Z, 3 of them on the PIC. On the PIC, you should know that we didn't really talk about the indirect registers, so we didn't really hold you responsible for those. But you should know about the W register, the bank select BSR, the PC latch high, and the program counter low, the PCL, which is how you write the 15-bit program counter. You should know that the BSR is 5 bits, the PC latch high is 7 bits because the program counter is only 15 bits, it's not 16 bits. And then the status register. So those are the ones you should be aware of. Okay, let's see, what else? We've covered a lot of this. All right. So you should know that you have a 3.3 regulator and a 5.5 regulator, and you should know that the way we hooked it up, the switch actually switches between using the battery input to drive the regulators, or the power coming from the header. Actually, the power coming from the header doesn't drive the regulators. It just goes right to the power selector. And you have a 3-pin power selector. You can jumper between 3.3 and 5. Although when you have the 2102 header plugged in, and you actually look at the voltage ratings for the 3.3 volts, it's usually not really 3.3. So apparently that's not really very well regulated. I think we talked about this, but just to remind you, we don't, when we have inputs, normally we have, unless the pin's driven by a gate that's either high or low, if it's driven by a switch, then we normally have to put either a pull up or a pull down on it, so that when the switch is open, we're still asserting a high or a low on that pin, and then when the switch is closed, we're dragging it all the way down to ground or all the way up to VCC, depending on the opposite of the pull up or the pull down, in order to drive a 1 or a 0 on it. So make sure you look at those circuits. Make sure you can correctly draw that. You should know that if your battery's hooked up, it's still connected to the regulators, and it will draw some power even if your board's turned off. So your battery will eventually run down to 0, because the linear regulators do consume a small amount of power just when they're connected. You should know a little bit about the debug features. Maybe on Thursday I'll do a little demonstration of the Microsoft Code Configure. I'll try and do that on Thursday. Because I don't think very many of you used it, right? How many of you actually use the MCC? Probably almost nobody, right? Okay, 1 or 2. That's good. So so I'll do a little demo and just show you what is available, because it is real powerful. And if you do any more coding with your PIC, you might want to install the MCC and actually utilize it. So we didn't do any things with the watchdog timer, but somebody tell me what is the purpose of the watchdog timer, or in the case of KL25Z, they call it a computer operating, they call it a COP, computer operating properly timer. But so what's the purpose of that? Yeah, so it's to break you out of an infinite loop. Now, normally, you could get into that by just a bug in your code, but usually you get into it by some kind of glitch. You know, there's a little power surge and the processor hiccups, and the next thing you know, it accidentally branches someplace in memory that it's not supposed to, and it gets stuck in an infinite loop. And so, if that were to happen, especially in something that's deployed in a location where it's, you know, where you want it to self-recover, then without a watchdog timer or something, it's really hopeless to do that. When you implement the watchdog timer, you have to be smart enough, though, to reset the watchdog timer at critical places in your code where if your code's operating properly, it will reset the timer before it times out. But if your code's not operating properly, you won't accidentally get caught in part of that loop where you're resetting the timer, because then it'll never time out and reset your program. So you have to kind of pick those wisely. Okay, good. We didn't talk about sleep. So the watchdog timer is not about power management, but the sleep mode is. And so you should definitely have some sense that we often use in battery-powered applications. We often use the sleep mode in order to really conserve power. The classic example is say a USB or a wireless mouse, and the batteries in those suckers last for a year. Yet they've got LEDs in them. LEDs that are pretty bright, probably drawing 15 milliamps of current. Well, one little AA battery couldn't possibly last a year, put down 15 milliamps of current, 24/7, 365. So obviously, what's going on there is when you're not actually using the mouse, it goes to sleep, and it goes down to practically, microamps, maybe even nanoamps. So when it's down to that kind of level, its power draw is basically shelf life at the battery level, and the only thing it has to do, it has to have some way, some system has to be left on so that when you trigger some input by moving the mouse, it does wake everything up and allows it to start processing information again. So there are some things that something has to still be on, and almost all these chips allow for various levels of sleep. The PIC really just one level, but the KL25Z has multiple levels of sleep. Several different levels that at different levels, different amounts of functional blocks are turned on or off, and so you can get down to a very, very low level where you're literally down to sub microamp levels of current draw, and that really prolongs battery life. Okay. All right. I think that's. I definitely want you to be able to. If I ask you, I might ask you again to switch values in using the assembly language between registers X and Y using a scratch register Z. But if I don't ask you to do that, I might for sure ask you to write a for loop, or I might ask you to set a register with the proper configuration bits, or maybe. Or maybe to set a bit using a mask, or to clear a bit using a mask. So make sure you know how to set and clear. Remember, when we use a mask, in the PIC chip, we have to use, and in C, we have to use the AND operator, the bitwise AND, so a single ampersand, to clear bits, and we have to set our mask up with a 0 where we want to clear the bit, and 1s everywhere we want to leave the bits alone. Whereas when we're setting bits, we just want all the other bits to be 0 and 1s where we want to set the bits. And then if we're toggling, we want 1s where we're going to toggle and 0s where we're going to leave it alone. So those are the three functions you can do, set, clear, or toggle bits. And so you should definitely know how to create a mask, say in a 32-bit field or an 8-bit field, to set, clear, or toggle any bit in that field or any combination of bits. One of the questions I often ask is is generate a mask in some tris register to set every other pin as an input, starting with pin 1. Well, it's just crazy. This seems to be a very difficult task for students, and I've never understood what the confusion is. So how would you do that? Somebody tell me how you do that. How would you set all the odd pins to be inputs? So 1, 3, 5, and 7, and then all the evens, 0, 2, 4, 6. How would you set those to be outputs and the odds to be inputs? Say on the KL on the PIC, on 16 of 1829. Yeah.
Would you use ANS? ANS?
Well, so you can do it a bunch of different ways. If you want to set and clear bits at the same time, then you have to write the whole register. You can't really set and clear bits simultaneously. Unless you know what's there, then you could toggle some bits and stuff. But if you don't know what's written already, then you have to first set the bits you want to set and clear the bits you want to clear with the second operation, the second mask, or clear first and set second. Either way, but it would take 2 operations. But if you write the whole register, in this case, since you're going to determine every bit, you can write the whole register. So what would you write, say in an 8-bit register, what would you write to set 1, 3, 5, and 7 as 1s, and all the other bits, 2, 4, 6, 0, 2, 4, 6 as 0s? What would you actually write? What would that value be?
AA.
Yeah, I think that's right. So you do AA. No, actually, let's look at that. So the higher the bit, yeah. So yeah, it should be AA is correct. Yeah. So 0x AA, and that's going to do bit 7, 5, 3, and 1 are going to be 1s. So you would, and what do you do with AA? Do you OR it or do you AND it? Or do you just write it? You write it. You write the whole 8 bits into the register. And that then achieves 1s where you want them and 0s where you want them. If you just AND it, all you're going to do is set the 1s. You're not going to clear the 0s. If you OR it, you're going to set the 1s. If you AND it, you're going to clear the 0s. But you're not going to do both with a single command. And if you toggled it, you wouldn't affect the even bits, but you would toggle the odd bits, but you didn't know what was written there, so you don't know what you have when you're done. Okay. Alrighty. All right. Let's. I think that's probably all for the general. That's pretty much it. You should definitely know how to do a while loop in C, and then the equivalent in assembly. So if there's a bit in a register and you want to wait till that bit's clear, then you should kind of know what steps, how you could set that code up. And obviously you can do a bit test in assembly. In C, you have to mask off the bits you don't care about and just look at the one you do. Okay. All right. So let's go through modules, and then we'll finish the modules up. We'll work on them today, and we'll probably finish them up on Thursday. Thursday we'll also have. Hopefully our chairman will come, and we'll do a little award ceremony to the winners. So 1 team first place, 2 teams second. There are 2 teams in second place, 2 teams in third place. So we'll have 5, and then we'll have 2 honorable mention teams. So, so make sure you're here for that. And on Thursday, on Thursday we'll have one additional rule, just out of courtesy for our chairman. We'll want all laptops, all cell phones put away, all laptops under the desk, so everybody's paying attention. I know that could be difficult for some people to actually not be holding their cell phone in their hand, but that's going to be the plan. And if somebody doesn't comply, it's going to cost you a percentage point of your course grade. So we're getting tough. But we just want to have an honorable time for the people that actually, did well with their project, and to sort of honor our chair. Okay. All right. So let's go through the modules. So first, analog to digital module. So here's some things you need to know for the A to D module if you're doing that one. Then let's see. I should have probably kept up. Okay, so, yeah, all right. So we'll do A to D, we have 50 to do A to D. Based on the configuration bit you set in one of the configuration registers, ADCON 0 and ADCON 1. And there's a bit 7 is a right justified bit. I think it's an ADCON 1. What kind of conversion method does it typically use? So we've talked about this a number of times. So let me go through this. We've talked about this a bunch, but you should know this. So basically, here's your so you have a multiplexer on the input, and you have 1, 2, 3, 4. You know, you've got 12 channels plus some internal pins, and I think there's like 5 bits of address for this. And then say here's your input pin, and then say here's your input pin here, and then you've got it. You selected the right address for this pin, and so now it's connected, and this goes then to a sample and hold capacitor. And what happens then is there's a switch here that basically disconnects the capacitor from here. So initially the switch is closed, the capacitor is charging up, and I guess there's probably some resistor to ground here. I don't know. They don't really show that. And then what happens is once you've connected the thing, when you start the conversion process, the first thing it does is it opens that switch so the capacitor is no longer connected to the pin, which means the voltage of the capacitor should hold. And this is then connected to a comparator. And the other part of the comparator comes from the other part of the comparator comes from a D to A. And in this case, the D to A is actually a 10-bit D to A, even though the actual D to A driving your output pin is only 5 bits. This one's built into the successive approximation module for your A to D converter is a 10-bit one. And what you do is you set the higher order bit to a 1, and it's got 10 bits in here. Set this to a 1, and all the other bits are zeros. And so depending on what your voltage levels are, assuming you're going, say you're running your board at 5 volts and you're using VDD and VSS, so the 1 then would give you half of the 5 volts, or 2.5 volts. And so the 2.5 volts is here, you compare this to this, and then the output of the comparator is going to go back here, and it's going to change. It's either going to go into this successive approximation register if it shows that the input, that this value is lower than the input, it'll leave this bit set and set the next bit. If it shows it's the other way, it'll clear this bit and then set the next bit. And it just walks through all the bits till it gets to the least significant bit. It either leaves it set or clear depending on whether this is higher or lower than the value from the sampling capacitor. This is a very high impedance input, so that the very little charge is drained off the capacitor during this time. And then when this is done, then the result that's in this register then is dumped into 2 8-bit registers justified either left or right, and that's what you read. So that's how that works. So if you present say you're running your chip at 5 volts and you're using, or even say 3.6 volts, and you're using VDD as the high reference, then if your input is 3.6 volts, what would you expect to read? What would you expect the value in your 2 registers, ADRESL and ADRS high, to actually be? That 10-bit result would be, yeah, it'd be 1023. So that's the whole idea. And if you put in a 0, it'd be 0. And if you put in half the value of 3.6 volts, so what would that be? 1.8. Then you'd get then you get something close to 512. That's the whole idea. All right, you should be able to kind of think about that in your head. You should know. You can clock it at about the rate. you set up the A to D clock that drives this module based on the system clock, and you can clock it at about 1 megahertz. So if you clock it any faster, it doesn't really get a good conversion done. If you clock it slower, then it takes longer to do a conversion than you really have to take. So you want to clock it at about 1 megahertz. But that does limit the bandwidth you can convert, because it takes about 13 clock cycles. 1 for each bit, so that's 10, plus about 1 to get this disconnected and set up, and then 1 to dump the information in and be ready for the next conversion. So the fastest you can do it, it's about 13 clock cycles at 1 megahertz, or 13 microseconds. And you can roughly guess about how that leaves you up bandwidth-wise. If you have a signal that's not suited to directly input into your A to D converter because it has positive and negative voltages in it, or maybe it has a bigger range or a much smaller range than your converter is running at, what can you do to fix that? How would you approach that? Well, so go ahead. You condition it, typically with an op-amp, although there are other ways to do it, but typically an op-amp would do it. You can use a voltage divider, but you have to be very careful. If there's much current running through the voltage divider, it'll screw up the relative voltages on your resistor ladder and make it create nonlinear results. Okay, let's talk about the PWM. So, what are some advantages of using PWM? What? Go ahead. Okay, so one of the questions I usually ask about PWM is, what determines the maximum voltage that your PWM outputs? So it turns out it doesn't have anything to do with duty cycle, right? It's the value you're running your chip at. So if you're running your chip at 5 volts, your maximum voltage is always 5 volts. What the duty cycle controls is how much of the pulse repetition period, what percentage of that period the voltage is at 5 volts, and what percentage is, obviously, where it's 0, obviously it's going to be 100 minus the percentage where it's 1 or 5. So that's what we call duty cycle. Duty cycle is always a percent, and it's a percent of the whole period. Now, when it comes to servos, the servos are specified to actually require a 20 millisecond period, but they'll often work down to maybe 11 to 12, or maybe even a little bit lower, maybe 7 to 12. But you still have to have a period, and in that period, your pulse has to vary from 1 for, say, full clockwise to 2 for full counterclockwise, and 1.5 would be in the neutral position, something like that. All right. Well, anyway, but then the rest of this period expires, and then it starts over. And it turns out if you just take a servo and you power the power pin, ground the ground pin, and then you just put a control voltage of 0 on the control pin, or 1, it doesn't make the servo go full scale or part scale. It doesn't usually move the servo much at all. It really wants to see a pulse. And that's how it's got a pulse, essentially has a square wave to voltage conversion module, and that's how it generates the reference to adjust the servo. But obviously, we can use PWM with lots of other things besides servos. What's one of the real advantages of PWM? Why do we use it? Why do we use it, for instance, with say with H-bridges, or why do we use it with when we want to change the brightness of LEDs?
Because the PWM has a really good control over ranges, so you can get exact ranges instead of getting very weak ranges or something like potentiometer. Yeah,
that's right, because some things are very non-linear as you change the voltage from 0 to its maximum operating voltage. Like an LED, as you change the voltage from 0 to say 2 volts or whatever it is. The problem is that the LED has a fixed voltage drop across it, and it depends on the color of the LED. Maybe the red and green are doing maybe a 1 volt or something like that, 1.2, and the blues and the whites are usually, and some of the weird colors are something like maybe 2.7, maybe even almost 3 volts. So if you try and just change the voltage, nothing happens till you get to that critical voltage, and then it'll start shining. Usually, you know, you'll see enough that you can see it. So it's hard to really have, you know, minimum brightness on it. And then as you go up, it usually gets very bright, and then you don't see much change after a certain point. Whereas with PWM, because you're giving it maximum voltage, but only for a certain percentage of each period, you can adjust the brightness through a pretty nice range. So kind of like you said. It turns out though, and so it's really because it's non-linear. The relationship between voltage and brightness of the LED is a non-linear relationship. But when you use PWM, you can turn it into a pretty much linear relationship. And the other thing that's nice is that there's very little wasted energy. With an LED, it probably doesn't matter, but if you're using it to, say, drive a heating element, if you use a rheostat or something like that, you're going to waste a lot of energy in the rheostat. If you do PWM, you're not wasting any energy at all. All the energy that flows goes to heating the element. It's just that you're able to control it electronically, so it's only flowing a certain percentage of the time. You do always have to take into consideration, though, frequency considerations. So for LEDs, if your pulse repetition frequency is too low, they'll be flashing, and if it's too fast, then the LED may not even be able to turn off between pulses, and so you'll lose your ability to control its brightness. So you do have to remember that frequency, things are very sensitive to frequency, well, within ranges. So motors, you're constrained to a much lower frequency with motors. You can only, you can only pulse a motor at certain frequencies. Above some frequencies, you're not going to get much effect at all. And then if you get below certain frequencies, then the motor will be real jerky, and your action won't be smooth at all. So there are frequency considerations. Okay. So let's see. So if we have a PWM signal, let's say our pulse repetition frequency is let's say it's I don't know, 500 milliseconds, okay? Or maybe we'll say 50 milliseconds. Well, let's say it's 5 milliseconds. Oh no, let's say it's 10 milliseconds. So that's 10, that's 20 milliseconds, and so forth. So every period has a pulse period of 10 milliseconds. So if in that pulse period we start off high and we go low, like right here, and then we start off high again and we go and we do this and we're doing that, so we just have a little bit of off time and mostly on time, what would you estimate the duty cycle is for that wave? Yeah, it's probably close to 90, right? Somewhere in that ballpark. And if it looked like this, if we only did it for half that, say, then, or maybe a little over further, what would you say that is? Yeah, or 50%, close to 50. So you should be able to look at a PWM wave and have a rough idea of the percentage. And I usually ask a question like that, and for some strange reason, that seems to be very confusing. But remember, the duty cycle is just the percentage of on time to the whole period. So the whole period is 100%, and if the on time is 20% of the period, then your duty cycle is 20%. Okay, now there are some fancy features like center aligned pulses. Our PWM on this mid-level PIC doesn't support that, but the KL25Z does. You can put the pulse so it's always centered in the pulse window. And why would you do that? Well, it turns out for high inductive loads, you get a few less extraneous side lobes, harmonics and things when you have it set up that way and you change the period. Some of the harmonics, you don't generate quite as much change in the harmonics and noise as you do if it's center aligned. But ours is restricted to being edge aligned. Okay. Good. And yeah, okay, that's probably good. All right. Real-time clock. I don't think anybody did that, so I'll skip that. Interrupts. Did anybody do interrupts? Did you?
I think there was.
Yeah, see. Yeah. Okay, one interrupt. We'll go through it quickly. All right, so the first thing on our low-level PIC, we'll probably focus all the questions on the low-level PIC because that's what you really did interrupts on, the PIC 16F1829. Okay, so in that chip, we know that all interrupts always, anything that causes an interrupt always jumps to location, I think it's location 4, yeah, location 4. And we have a number of things that can cause interrupts. There's a single pin that does what's called the int pin. This is a legacy pin, but we also have a new feature for this family of chips called the interrupt on change, which allows, I think, all the, it's C and
Just put B.
just port B, and it's A2.
Not on this.
Yeah, okay, let's look. I've got the data sheet. It's 2 ports. I forget which one always, but it's for sure 2 ports. Let's see. I have ports. Interrupt on change. The port A pins can be configured to operate as IOC, and on the 29, the port B pins can as well. Yeah, so it's A and B, not C. Okay, so anyway, yeah, here. Okay, so anyhow, so that is interrupt on change. And when you generate an interrupt, all interrupts go to that same vector. So if you have a couple things that are turned on to cause interrupts, then you have to go check interrupt flags in order to see what caused the interrupt. Let's see. So, okay. So when you go to an interrupt, there's a couple things that happen. One of the things is we want to preserve what's going on in the mainline routine. So we have special registers on this chip. On most chips, like your Intel chips, your AMD chips, the KL25Z, the information we want to save, some of it at least is pushed on the stack. But in this chip, we just have this one hardware stack, so we push the return address on the stack, but there's other registers that need to be saved too. We need to save the W register, we need to save a couple of other registers. We could make the interrupt routine do that for us, but that would take more time in the interrupt routine. So this chip has it set up to automatically do context saving for a few registers in special hardware locations. The implications of this are that you can't interrupt interrupts. So one of the first things that happens when you go into an interrupt, the hardware immediately disables all other interrupts. And so when you interrupt in your interrupt routine, you have to check and see what caused the interrupt, and that's what you have to take care of. If you only have one thing turned on, it's usually pretty easy to figure that out. But you don't have to worry about saving certain registers. They're already saved for you. They will be automatically restored for you. And I always forget which one it is, but the W register is one of them, and the BSR is probably one too. There's 3 or 4 of them. Okay, but the return address is pushed on the stack. When you execute the interrupt routine, your interrupt routine is not allowed to have any variables passed to it, and it's not allowed to have any information returned. And the reason is because you don't really call that function. That even though it looks like a function, it's never called directly from the main routine. And so if there are variables you want to change in your interrupt routine, you generally have to define those as global variables. On our PIC chip, obviously all the special function registers and stuff like that, the ports, all that stuff is global anyway. But But if you actually want to create a variable in your main routine and have the interrupt routine change it, then it has to be declared as a global, so the interrupt routine will have it. Or you have to provide some way for it to get to it. You could have a global pointer, that would be fine too. When you service an interrupt, one of the things you always have to make sure you do is clear the interrupt flag that caused that interrupt. Because if you don't, as soon as you return, you'll re-interrupt again immediately. And so almost always, the flag that caused the interrupt has to be cleared by the interrupt service routine itself. It's very uncommon for it to be automatically cleared in any way. That wouldn't really work. There are quite a few different things on the PIC chip that can cause interrupts. Almost every module has usually at least one thing that can cause interrupts, and some of them have multiple things that can cause interrupts. You have, so figure however many modules there are on the chip, almost every one of those modules can generate one or two or maybe even more interrupts. Then on top of that, you have the interrupt on change pins, and then the int pin, and then, so there are quite a few things that can cause interrupts, on this chip. Let's see. Typically, the interrupt service routines are something you as the user have to write. You might be able to find code somewhere on the web that might help you, but basically, you have to provide that interrupt service routine. That's not taken care of automatically. Okay, enough of that. LCD. So a number of you are doing LCD displays, right? How many are doing LCDs? Okay. All right, so let's talk about the LCD. So for the LCD display, you have, there's a typical 16-pin interface. Now some LCD displays are set up as 5-volt devices, and some are set up as 3.6-volt devices. So it's kind of nice to know which one you bought. Unfortunately, they look identical. It's really hard to tell them apart. And since I bought a bunch of each, and now they're all confused, so it makes it difficult. I'm going to have to work at labeling them better in the future. But in any event, there are several different ways, but fundamentally, however you use it, at some point you have to address the 14 pins that make up the interface, and then usually there's 2 additional pins to power the backlight. And so we had it set up so we did a parallel interface, and we also had it set up so we could do a I2C interface using that little PCF chip. And so those are kind of the 2 primary ways. The PCF chip has 8 bits that you can set. And so when you run this in one of either parallel mode or when you use this 8-bit PCF chip, you really need a bare minimum of 6 pins and 7 if you're going to use the read-write pin. And so that's 7 of those bits, and then the 8th bit is usually set as a bit to turn on or off the backlight. So that's usually how the I2C interface is set up. When you just do the parallel interface, you usually are going to drive 5 pins or 6 pins, or rather 6 pins or 7 pins, depending on whether you want to control the read-write line. So you always have to provide ground and power, and then there's a pin called the contrast pin, where it's really nice to put a pot on that pin so you can adjust the contrast and have some fine control. If you don't have a pot, you can just ground it. That works. And then you have the register select pin, the RS pin, which determines whether you're sending a command or data. You have the read-write pin. Normally, you're going to always write, and so you can just ground that pin in permanent write mode. But if you want to check the busy bit to sort of optimize the amount of time you have to wait before you can issue another command, then you need to be able to read it so you can check the busy bit. And then the next pin, pin 6, is the E pin, which is really the clock. It stands for execute or whatever. And you toggle that pin to latch in your command or latch in your data. And normally, there are 8 data pins. Normally, we only use 4 of them. And remember that the 4 that we use in our 4-bit mode are the 4 high data pins 4, 5, 6, and 7. So normally, we would just pull down through a resistor data 0, 1, 2, and 3. Remember a couple of things about the chip. There are certain commands we have to give and various things. But the minimum connection that we can use would be the RS pin, the E pin, data 4, 5, 6, and 7. And then obviously connecting power and ground, but those don't have to come off the microprocessor. When the chip is first powered up, it's in off mode, and it's automatically in 8-bit mode. And so we normally issue 3 commands of 30 to kind of make sure everything's synchronized, which basically gets it in 8-bit mode and gives it time to power up and everything. Once we've done that, then we can put it into 4-bit mode and then begin sending our instructions in 2 nibbles at a time. We always send the high 4 bits first and then the low 4 bits second. And you have to send 2 commands or 2 data bytes to complete a transmission. And you don't want to send one and then forget and then not finish it and then go back and try and send another one, because it'll be stuck halfway using half of your first command and you'll get out of sync. But fortunately, you can always go back and issue 33 times and get it synced back up. So usually you want to set it up and you have to send, you have to turn it on, you have to turn on the cursor typically, you want the cursor on, although you don't have to, and you typically want it blinking so you can see where it is, although once you have your application all set up, you might turn that feature off. You can also change whether auto increments or auto decrements after each character you send. And you have to keep in mind, you can set what character the address is set to. You can clear the display. You can clear the display and set the cursor to the home position. There's a bunch of different commands you can give. You don't have to memorize any of those commands. You just have to sort of have a general idea that you can do different things with it. Okay. I think that's it. So just kind of knowing what pins are available and kind of the steps to get the thing going, that's sufficient. All right, let's see, temperature sensor. So there are a whole bunch of temperature sensors out there. Some of them use just output a voltage. Some of them actually have an I2C interface. Some of them have what's called a one-wire interface. Some of them actually have addresses, so you can actually address them. And each your temperature sensors can have its own address. The ones we worked with were sort of like the LM34 and the LM35 are the one that's on the little board you guys plugged in. That's a microchip sensor, and I forget the nomenclature on that one. And those work in a very similar manner. So many of these temperature sensors that output a voltage are pre-calibrated, so you're pretty much guaranteed, given a voltage level, what that temperature correlates to. And those are a whole lot easier to use. If you use the internal sensor on the PIC, then you do have to calibrate it, so you can measure the voltage with your A to D converter, but you won't know exactly what temperature that corresponds to until you calibrate it using a 1-point calibration method or even a 2-point calibration method to get a better range. Remember that these temperature sensors, the ones at least we use in lab, all send out an analog voltage, including the on-chip one and the microchip part and the LM34, LM35s. Some of them go all the way down to absolute zero, some of them don't. The microchip part we use doesn't. The LM34 does. So we have to take this voltage coming off our temperature sensor and feed it into an A to D channel. Now, if you get a temperature sensor that has a different protocol, like one that say works on I2C, then you would maybe get a digital value out of that temperature sensor. There's some that are set up for SPI mode even. So there are numbers of different ones, and they do have different accuracies and precisions. Most of the ones we use, though, work based on the idea that a voltage across a bipolar junction actually is affected by temperature in a pretty much linear way. And that's pretty much what we use. Whether it reads in Fahrenheit or Celsius, you can obviously do a conversion in your microprocessor using math. So there may be a limit to how cold or how hot it can go, though. Obviously, there's a limit to how hot it can go before it destroys itself. And there may be a limit to how far down it can go cold-wise. But some of them are set up so they can go down to absolute zero. The internal PIC sensor, you should know that it has some voltage limitations. If you're running your chip at 3.6 volts, then you can't use it in the 4-junction mode. You have to use it in a 2-junction mode. And there's some internal bits to set to turn it on and to set whether you do the high range or low range mode. And that internal temperature sensor does require calibration. Okay, GPIO. So let's talk about that. We mentioned it briefly earlier. So first off, what is the source and sink capability of your typical GPIO pin on your PIC 16F1829? 25 milliamps, and it can source or sink. But generally, you want to sync things because if you source things, all that voltage has to come in the VDD pin, and it has a slightly lower budget than all the current going out. The ground pin has a little higher budget, so you generally want to sync stuff if you can, because then the current provided to your device comes in from an external pin through the device and then is sunk into your microprocessor pin and goes out through the ground pin on your chip. So the ground pin does have an overall max current out, but it's bigger than the max current in. And that's just because of trace sizes and everything inside the chip. So normally we do try and sync stuff if we can. Or if you have, of course, a load that exceeds the load power of the chip, then you would obviously have to use a BJT or a FET or something to do the higher power. Remember, when you hook up a switch, you can't leave a pin floating. So you have to have when the switch is open, there has to be something pulling that microprocessor pin high or low. Yes, they do have internal weak pull-ups. On some chips, they're sufficient. On our PIC chip, they're really not sufficient for that purpose. So you really do need an external resistor. And usually we use something like 10K. That's just kind of a nice round number, but anything in a pretty wide range would work. And then when you close the switch, you're going to drive it hard the other way, directly to ground or directly to VCC. So just sit down and go through and pay a little bit of attention. You should know that one of the powers of GPIO pins, if you need to implement a protocol that you don't have a module for, you can usually create that in your software using a GPIO pin. And the nice thing about GPIO pins, well, one of the things we do in Micro 2, we have a touch sensing panel that we use. And on that touch sensing panel, it has two resistive coatings. So it's got two coatings that are stacked on top of each other, and each one has a resistive coating smeared across it. And on one panel, it's got an electrode on one end and the other end, and on the other panel, the electrodes on the top and the bottom. And so what we do, we have these four leads coming out, left, right, top, bottom, and there's little teeny spacer dots in between that you can't see, but they're there. They keep the surfaces apart. And then when you touch it, this is a resistive touch panel. They're also inductive and capacitive. Most of your cell phone stuff is capacitive. iPads, iPhones, Samsungs, they're all pretty much capacitive. But there's a bunch of stuff that's touch as well. And anyway, resistive. And this is one we're using is resistive. And the way it works is you configure GPIO pins to make this positive and make this minus, and then you read the bottom panel with your A to D. And then you switch it around. You make these inputs, connect that to the A to D, and you drive this positive and this one minus. And when you scan back and forth between those two modes, you can measure a voltage for the X and a voltage for the Y that gives you the relative voltage provider where you have that touch, where your finger was pressing down. And in order to do that, though, you have to take GPIO pins and switch them from outputs to inputs really rapidly to make that work. but they can do that. They're perfectly adept at doing that. So there's a lot of power with these GPIO ports. They can do a lot of different things. There's even a way you can tell on the PIC if your GPIO port's shorted. If you try and drive, here's your PIC, if you try and drive a pin, you write a 1 to the pin using the latch, and you have it set as an output in the tris register with an O, with a 0, then there should be 5 volts on this pin. But if you actually pull that pin straight to ground and you read it with a port command, the port A command will actually read what's on the pin. If it's short of the ground, the pin will read 0, even though you're trying to drive it to 1 out of the flip-flop that's associated with that pin. And you can actually detect that that pin's shorted. It's kind of cool. So there are a lot of really neat things you can do with GPIO pins. So remember the difference between the lat register and the port register. The lat register writes and reads the flip-flop, and the port register writes the flip-flop but reads what's actually on the pin. Remember that if you're in analog mode and the ANSEL bit is set, then you will not get an input value that you can read because it's blocked off, the digital function's turned off. And if you want to use the analog function, you have to have that analog bit set, which it is by default. Let's see. You should have an idea of how many pins are available in the various ports on the PIC. And of course, when you write a 1 to the pin, it's going to output VDD. When you write a 0, it's going to output ground. Okay, and yeah, I think that's it. All right, how are we doing? So, I2C. Did anybody do I2C? I think so. Let's see. Maybe not. Yeah, I don't think anybody did I2C. All right, moving on. We'll do one more and then we'll quit from there. Let's see, did anybody do timers? Yes. Yeah, there were several people who did timer. Okay, so let's talk about the timers real quick. We'll finish on this. Okay, so on the PIC 16F1829, there's several different timers. There's timer 0, there's timer 1, and there's timer 2, 4, and 6. There is no timer 3 and 5, interestingly enough. Some of the chips in this family do have timer 3 and 5, and some of them have more 16-bit timers, but there's only one 16-bit timer on this chip, and that's the timer 1. The timer 1 also uniquely has a timer 1 gate, so you can actually turn the timer on and off with an external pin, and that's actually very nice if you're trying to measure the length of a pulse. You can also do that with the CCP module and timer 2, 4, or 6. So timer 2, 4, and 6 can be used independently, or they can be used in association with the capture, compare, and PWM module, the CCP modules. You only have 3 timer 2, 4, and 6s, but you have 4 modules, so you'll have to share at least one of the timers. Although that's not a big deal. Usually you can do all the PWM pins with the same timer if you want. The timers 0 and 2, 4, and 6 are all 8-bit timers. But they do have prescalers and postscalers. However, for some functions, the postscaler, like for PWM function, the postscaler on timer 2, 4, and 6 can't be used, just the prescaler. So it's good to know about how prescaler works, how the postscaler. Typically, you're typically driving these with system clock, but it doesn't have to be that way. You can actually drive some of these timers with external clocks, and then so then they can tick along at whatever value your external clock is driving that. You can set up a pin to do that. These timers basically don't have the up-down count capability. They do on the KL25Z. They do have up-down capability, but these only count from 0 up. When they hit the max value, they'll automatically roll over. Or if they match the period register that's associated with them, they'll roll over on that too. And you can set them up in several different ways. So let's see. You obviously typically use timers to create, measure the intervals of time. But you can also do this with for loops. It's just that a timer runs independent of the rest of your code out there as a module, independently counting away, and it gives you a little more accuracy for counting things than if you're actually using a software loop that might get interrupted, that you might have a branch in it from time to time, where it could be affected potentially by just the way the code is. So typically your timer is going to give you a more precise count than say a software loop would. Yeah, I think that's it. Well, why don't we quit with that? I'll finish going over all the modules then on Thursday, and we'll also do the awards on Thursday. So we'll see you then.